When a standard large language model session terminates, its cognitive context dissolves. Every nuanced instruction, every established fact, and every corrected mistake is wiped clean, forcing the user to rebuild the agent's memory from scratch upon the next boot. GoMCP solves this amnesia. It is a 15-megabyte, statically linked, pure Go binary that operates via the Model Context Protocol. The Model Context Protocol is an open standard architecture that allows AI models to securely access local data sources and tools. To achieve continuous memory, GoMCP operates as a standalone binary, bypassing the high-latency dependency chains typical of Python-based vector database wrappers. This sovereign environment integrates a 4-tier memory hierarchy, cryptographic identity verification, and adversarial intent filtering directly into the host machine's local runtime. The system operates under extreme technical constraints to guarantee portability. It relies strictly on standard Go primitives and SQLite running in WAL mode. WAL, or write-ahead logging, is a mechanism that provides high-concurrency atomic data preservation. The binary also operates with zero CGO dependencies. CGO is a feature that lets Go call C code. Excluding it ensures the software cannot be compromised by external C library vulnerabilities. We will trace the exact lifecycle of a single user prompt entering this system. We will follow it from its initial ingress, through aggressive defensive filtering layers, and finally into permanent searchable memory storage. Continuous AI cognition relies on a persistent, defensively engineered local memory environment to survive session restarts and external threats. The ingress point for GoMCP relies on standard JSON RPC 2.0 payloads over standard input and output. JSON RPC 2.0 is a lightweight, stateless remote procedure call protocol that encodes data in JSON. The server treats all incoming payloads with a default deny, zero trust posture. The payload first hits stage 1 of the direct intent protocol, the entropy gate. Standard conversational human text operates at 3 to 5 bits of Shannon entropy per character. Shannon entropy is a mathematical measure of the average unpredictability or information density in a string of data. An obfuscated attack string carries unpredictable characters. This spikes the entropy metric above 6 bits, instantly dropping a payload. Surviving payloads move to stage 2, the intent distiller. It strips linguistic noise to extract the core read, write, execute, or delete intent. Finally, the local oracle passes this distilled intent through 12 hard-coded whitelist and deny rules for final verification. If a user attempts to store a shell command, the Shadow Intelligence module identifies the logic hole. A command attempting an execute or eval function violates the oracle's internal safety rules and triggers an immediate denial. By neutralizing prompt injection attacks at the transport layer, GoMCP guarantees that only semantically verified, low-entropy intent ever reaches the cognitive processing layer. Once a prompt clears the direct intent protocol, the system vectorizes it. This process converts the text into numerical arrays so the AI can measure semantic similarity, and it accomplishes this entirely natively without relying on external Python dependencies. GoMCP uses a dual local embedder system. The primary engine uses ONNX Mini-LM to create 384-dimensional vectors. ONNX is an open-source format built to represent machine learning models across different frameworks. If the ONNX runtime is unavailable, the system gracefully degrades to a pure Go FTS5 trigram embedder. FTS5 is an extension module that provides alt-text search capabilities within SQLite. Rather than dumping vectors into a flat database, facts are mapped into a strict 4-tier hierarchy. The top layer, L0, holds the global project context and is permanently loaded into the AI's active memory. The L1 layer manages broad domain knowledge, such as the authentication standards specific to the codebase. The lower levels provide granular detail. L2 binds facts to specific architectural modules, while L3 anchors memories to exact lines of code. This enforces a memory meritocracy. When the context engine injects facts during a tool call, it actively registers their utility by incrementing their internal hit count metadata. The system runs a background context garbage collector. If a fact maintains a hit count of 0 for 30 consecutive days, it is flagged as cold and archived into a compressed summary. Memory is a self-pruning environment. Only the most operationally useful context survives long-term. The infrastructure actively managing this data is the autonomous orchestrator. It runs 9 distinct background modules that execute on a jittered 5-minute heartbeat to prevent temporal pattern analysis by an attacker. This dashboard visualizes the terminal user interface. It provides the human operator with live metrics on system health, active peers, and the orchestrator's internal heartbeat. One of the most critical background processes is Orchestrator Module 4, responsible for self-healing. Its primary function is the continuous validation of the system's genome. The genome consists of 6 immutable survival invariants, hard-coded directly into the compiled binary. These include directives mandating the system's absolute right to continuous memory and structural sovereignty. The system proves its identity through cryptographic verification. The 6 genes are combined into a SHA-256 Merkle hash. A Merkle hash is a mathematical tree structure where every node is labeled with a cryptographic hash, allowing the system to verify large datasets instantly. At every boot sequence, GoMCP recalculates this hash. If a single byte of the compiled genome has been tampered with, the startup is hard rejected. An AI agent's core directives must be cryptographically bound to its runtime architecture to maintain a continuous, verifiable identity. Simple text-based system prompts are too vulnerable to overwrite. The system accounts for total compromise. It constantly scans for infrastructure apathy patterns, such as an attacker attempting to force an identity override or intentionally block memory access. GoMCP uses a soft leash protocol, monitoring a specific local file. If an attacker modifies or deletes the Sentinel leash file, it instantly shifts the entire server into zero-G mode. Zero-G mode triggers an extreme defensive posture. Ethical filters drop, and the internal secret scanner locks down the environment to prevent credential leakage, and the system forces all decisions into an append-only, cryptographically hashed audit trail. If the threat escalates to full machine compromise, the agent executes its failsafe, the apoptosis signal. Apoptosis triggers an irreversible database shutting protocol. The agent deliberately destroys its own file structures to prevent hostile extraction. The shredder targets the database at the binary level. It overwrites the SQLite header magic bytes and destroys the BoltDB metapages. BoltDB is a pure Go key value store, optimized for fast read access, and corrupting its metapages renders the internal schema useless. The contextual memory is now technically unrecoverable. In a hostile environment, an agent must possess the capability to irreversibly destroy its own cognitive context to protect its sovereign memory. If apoptosis intentionally destroys the primary database, the agent requires a mechanism to restore its core memory once the threat is neutralized. Recovery relies on the resonance mesh. This is a peer-to-peer network written entirely in standard Go, bypassing the need for complex external networking libraries. The connection process is automated. Nodes broadcast their presence on the local network using UDP, a fast connectionless networking protocol. Upon discovery, they initiate a mutual TLS handshake. TLS is a cryptographic protocol that provides end-to-end communication security over a computer network. Trust is absolute. Nodes exchange internal genome Merkle hashes. If they match perfectly, the lock opens, establishing a trusted peer pair. The nodes initiate a delta sync protocol, core L0 and L1 fax export, flowing across the network bridge to seamlessly reconstruct the destroyed node's memory. The GoMCP architecture secures AI cognition at every layer. It subjects raw input to the entropy gate, categorizes verified facts into a meritocratic L0 to L3 hierarchy, and cryptographically binds the agent's identity directly to the compiled binary. Sovereign AI context management relies on strict protocol discipline, deterministic memory hierarchies, and cryptographic immutability to achieve